Okay. Welcome everyone. Thanks for coming to week 3 of our beginner track. Thanks for being on time as usual as well. This week 3, we'll be going over linear regression, which is one of the most, famous as well as well known and pretty widely used in a lot of places, a model for machine learning. And so, yeah, quick notes is that if you're following along on the membership portal for attendance, the code for this week is Serbia. And if you keep track of all the codes for the whole quarter, there's actually a cool pattern in the codes. So I'll keep that in mind. And next week, if you guys don't have any ideas, I'll give you guys a hint so that it might make a bit more sense. But this week is Serbia. And also Jensen put the link to the feedback form in chat, but it's right here as well. And so we really appreciate you guys' feedback. So if you guys can fill it out again this week when you're done, or when after the workshop, that'd be really helpful as well. Lastly, if you haven't joined the Discord yet, it's a great place to ask questions as well as find our get links to our YouTube videos after they are posted on YouTube. As well, you can ask questions as well as we have office hours there as well. Okay, so for today's content, we're starting out with a good example for why linear regression is important. We're going on to something called a hypothesis function, which is pretty useful for linear regression. We'll dive a little bit into the math so that we can get a good background about how it works. Don't worry if you are afraid of math and don't like math. We'll try to go slow, as well as we'll always be there to answer you guys' questions. So don't be scared by the math. It's not. I would say it's not too bad, but then if it is too bad for you, if it is like not fun for you, we'll be link to the slides. Jensen posted the link to the feedback form, and the form has the link to the slides, I think. Maybe we forgot this week. I don't know. If we did,
should be in the form.
Cool. Yeah. So yeah, if you go in the form, yeah, cool. Awesome. Yeah. So let's go on to our example. So for why we want to linearly regress, I guess, or find a regression. So I guess a really important topic to all of us right now is how well will someone do on their midterm? And so it's week 5. A lot of us have midterms either last week or this week or maybe next week. And so it's important to think, I guess not important to think about, but we all kind of care about this. So let's think about how we can break this problem down into a more feasible, a simpler problem. And so with that in mind, to predict your midterm performance, what information might be helpful? Like what type of things? Like for example, I would say like the number of hours you spent studying is important indicator of performance. But in the chat, or if you want to unmute, it's also works. Just suggest some ideas on what's important for these type of things. Okay, so I see Maxwell said lectures attended. Yeah, that's awesome. That definitely makes sense. And Eva says past grades in the class. Definitely makes sense as well. Like if you failed the class in the past, you might be worse off for this midterm. So those are some great examples of features. So we'll get into it soon, but this is some important information that you might want to use to predict performance. And there's some others as well. You guys had some of these as well, like time spent studying, lecture hours attended, time spent sleeping, things like that. Those all can be compiled and used to predict our performance on midterm. And so there's actually a term for this information. It's called a feature. And so each of these types of information is called a different feature. And so each thing is like its own feature. So you might have like 10 different features that you might use to predict for performance, or more or less, depending on your model. And so as a result, we have like a relation between the features and our score. And so based on our features, we're trying to predict a score. So that means our score predicts depends on our features. And so because it's a linear relation, it's a linear regression. Each of these features is going to be multiplied by a number. which we'll get to later. But it's important to think about as well, like how these features actually relate to our midterm. So on that note, are they positively or negatively correlated? So for example, if you have a lot of lectures attended, that means your score will probably go up as well because you know the material better. And so you'd say that lecture hours attended or lectures attended is positively correlated with your midterm score. On the other hand, you might say like hours spent on the beach, for example. Actually, I don't know if that's like negatively correlated, but let's say you spent like 100 hours on the beach in like 1 week. Then you're probably going to do worse off on the exam. So I would say that feature is negatively correlated to your midterm score. And so this is important to think about, like how our features are going to relate to or impact our midterm score. And so from there, the question is, how would you model this? And you guys probably guessed it, or it's going to be linear regression in this case, but there's other ways to model it as well. But linear regression is one of the most common ways to model this type of problem or these type of problems because of how simple yet fast and relatively effective it is. And so just summarizing a lot of that as well as like making the terms pretty clear. We talked about features. So a feature is like some property of like the object or situation that impacts the target. So basically the score. So for example, the pass grades in the class is a property of like a student or the situation of like the class, the student in the class that impacts how you're going to do on the midterm, which is the target. And so for example, time spent procrastinating is a feature. So like if you spent a lot of time procrastinating, that obviously impacts how you're going to do in the midterm. If that makes sense. And then the second part of that is the target / label. Both terms typically work and are used kind of interchangeably. But basically the target is like the true value or like the actual value of what we're trying to predict. And so that could mean like, let's say we have like an example student, right? And so this example student spent 30 hours studying, went to like 9 hours, like 10 hours at lecture, and like went to the beach for like 15 hours. And they got like a score of 77%, right? In this case, those features would be the features I listed first. And the target would be 77%, which is what we're trying to predict, because that student actually occurred. They went to the midterm in the past and they got the score. And so we can use their true data to figure out or to help our model predict. And so in this case, the target would be the student scores. All right, moving on. Oh, actually, before I move on, just any questions? I don't want to go too fast, so that, yeah. All right, cool. If you have any questions, just feel free to interrupt or write them in chat. All right, so moving on, we have our features, we have our target. And so we want to figure out how we're going to represent this on a bigger scale, because we're going to have like maybe like 1,000 students and like 1,000 scores. So you don't want to have to like, you want a way to like represent it in like a more compact form. And so to do that, we're going to use matrices, no surprise. Arrays of arrays are really useful in general. And so in this case, each row of information is basically the information for one student or one test taken. And so as you guys can see here, we have 4 students in our small data set. And so the second example, which we've highlighted right here, this student right here had a pretty high homework score of 95%. They had 15 hours studied and 19 hours in lecture, and they got 90%. And other students did different things. And you can see that this student probably had the highest like numbers for all these things, and they had the highest score, which is a pretty good correlation that we can see. But the important thing here is that the row has all the information for one student. Meanwhile, the column represents all the data for one feature. So as you guys can see here, the first column is the homework average, study hours a second, then lecture hours, and then usually like one of the columns or a different vector or a different matrix entirety has the target data. So in this case, the fourth column is the target data, which is midterm percent. And so this is usually called y, small y, the target vector. just because it's like y equals mx plus b is like linear regression. So y is used in general for predictions or the true values or labels. All right, so to model this relationship in our data, what we want to do is use a linear model. And so a linear model basically means that every feature is going to be multiplied by like a coefficient of sorts. So like you guys know, like a linear, like a line in like two-dimensional space is like y equals mx plus b. And in this case, your m would be your coefficient and your b would be your intercept. And so the same thing applies to more features, except they're going to be in higher dimensions. So you might have like an M1 and M2 on and on. So the important thing to figure out here is you want to figure out all of the M's, all of the M1, M2, the coefficients, and also want to figure out B, which is the intercept usually, and we'll find out the terms for this later. But it's important to think about how we model this. And so going back to how ML works again, it's really important to consider the difference between ML and typical programming. So in this case, we're trying to figure out midterm score by basically learning a pattern between different features and the target score. And so we're not actually like explicitly writing like a model for the code to follow. It's more that we're letting the model learn like different parameters to find like the optimal model. Yeah, so the big difference is that we're not programming everything by hand. We're actually letting the model learn by itself by taking in data. And so you can see that here in this nice little graphic, that traditional programming, you take in data, you take in a program. So maybe like you have like a program to figure out the cost of like a bunch of fruits, right? So you might have like your data might be 5 apples and 5 oranges, and then you might pass in like each apple takes $5, and each orange is like $1. So you might pass that in and you get results. In machine learning, maybe we want to figure out like the cost of an apple and a cost of an orange, and so we'll pass in like the total cost. We'll pass in like total cost. So we'll pass in like what the inputs were, and we'll figure out a model. Basically, it's not the best analogy, but the important thing is that we're passing in both the inputs and the outputs, and from that figuring out like a good relation between those two. And so just a quick dive back into the pipeline. We'll be going mostly over training and testing today. The other steps are really important as well, but I think this is already a lot for one workshop, so we'll just go into these two for now. And so now let's put it all together and like actually like go into like a formal definition of how these things work. So first thing is a hypothesis. And so we want to basically figure out a function that will, given like a feature as an input. So like, let's say we're given like number of hours studying, number of hours at lecture, pass grades in the class, like number of hours spent procrastinating. We want a function that takes those as inputs, and as a result, outputs the target, or outputs our midterm score in this case. And so we call this function the hypothesis. Basically, it is a model for like our pattern that we're interested in for our data set. And so it's going to basically encompass all the important like relation between each feature and the output score. And so in this case, we're going to call our hypothesis y hat. So it's like this like y with the hat on it. And as an input, it takes in the features. So like it'll take in like, for example, x1 might be hours studied, x2 might be lectures attended, and like xn might be past grades in the class. And so he'll have like n inputs, and so they all get passed into the hypothesis, and it'll do some stuff with it and pass and give an answer. And so now the goal is to figure out what y hat is. And so I would say that the big hint here is that it's a linear relationship, and so that helps a lot figuring out y hat. But since we're using, oh, I forgot the slide existed, so let's talk about a model first. But first, the model. I think a model is like a term tossed about a lot that doesn't really have like a strict definition. But I would say the model generally is like a way of like how like a machine sees a situation that's happening. So like how it like relates features to a target. So how it relates like your hours studied, hours spent in class to your answer or like your score in the class, that type of thing. And so yeah. All right. So going back to linear regression, we have our features that are like things like hours spent studying and studying on homework and just studying in general. And these features in general are proportional to the result, which means that we can use like a linear background, a coefficient to get to our end score. And so we've already seen correlation things. And so yeah, either negative, positive correlation. So like for example, negative correlation between hours spent procrastinating and score, but like a positive relation between lectures attended and score. And so, yeah, a linear model is a good choice because multiplying that coefficient is the same thing as looking at proportionality. And so this is the magic point where we get to our actual equation for our linear model. And so this is why our hypothesis. And so you've probably seen like a thing similar to this before. Think of this W1 as a M, and you'll see Y equals MX plus B in the first chart. But since we have X to the, we have N inputs from X1 to Xn, you actually need to have a weight for each of these inputs. And so we'll have W1 through Wn, and we have our B term here as well. And we'll define what these actually are called, but they are pretty intuitive in terms of what they mean. And so, yeah, this is our hypothesis. Yay, we got to our epic function. All right, so now that we have our function, we want to be able to do this on like a large scale. So let's say we have like, these are our inputs. We don't want to actually like go like, oh, we have a variable called x1, a variable called x2. We don't want to have like these explicit variables out here. So to make it more efficient, we use vectors and matrices. And so in order to represent this hypothesis as a matrix, what we do is we basically represent these things called the weights that we want Wn as a vector. And so given inputs x1 through xn, we can actually multiply the two vectors, and that we get and add our b term to it, and then that's what our result is. And so if you guys remember multiplication of matrices, you'll remember that basically it's like horizontal row times vertical column, a horizontal row of the first matrix times vertical column of the second matrix. But in this case, because they're both like so this is a 1 by n and this is an n by 1 matrix. It's pretty straightforward. It's just x times n, x1 times w1, x2 times w2, all the way to xn times wn, and that's our sum. And then we add b to it. And so this gets us the same thing as we have above. And so it's important to have this though, because this gives us a really compact version of our equation that we can use at a much faster speed for calculations. And yeah, X will have, what Jensen said in the chat. For example, like if you have like 100 students, you might have like 100 rows of this. And so instead of having to do this like 100 times, you can just do it all at once with a matrix instead of a column vector. I think we'll see this later, but it's important to note that matrices in general are the way to go because they're a lot faster and they make things more concise and compact. And so let's dive into the parameters. So, this should have hidden before. I guess my transitions didn't work out, but no big deal. So the first thing is our row vector for the input. And so this is just all the features for one student. So this x1 might be like one student's like hours spent studying. So maybe it's like 10 or something. And same for the other one. So it's basically all the n features laid out in a row. The weight vector is an n-dimensional column vector. So it goes up like straight down. And basically it's a weight for each of these features. So like how much does each feature impact our score? So like, for example, maybe like, let's say hours spent studying is really important to get through well in the midterm. Maybe W1 will be a lot bigger than like W4 if W4 is like hours spent, something less important, like hours spent on like brain games or something. I don't know. That like helps you in general, but not for like the class or something. So like in that case, W1 will be greater than W4. But in general, we have our weight vector, which consists of all the weights for each of these inputs. And lastly, usually B is called the intercept in like math, but in machine learning, it's called the bias. And so it's basically, it's a real number, it's just a number. So it helps us get to like a more like, basically it helps us like fiddle with the output range of our data. And so looking at the weights first, I guess the weights in general, like the weights are W1 to Wn, but B's also might be talked about as well, because W1 to Wn and B are all learnable parameters of our model. And so this is important because this is where the ML comes in, because we're not telling our model like this is what the parameters are. We're like giving it a bunch of data, and it's going to learn from that what the best W1 to Wn are and what the best B is as well, to like capture all the data in a good model. And so what you can note is that we can change our like the output of this function by like moving around W1 to Wn. So like if W1 is 0, then we don't care about x1 anymore. But if W1 is like 100, now we really care about x1. So there's flexibility to learn about new relations with this type of coding practice, like with ML in general, because it can learn different types of data. And so it's more flexible and like it's easier, like it can model more complex things than like humans can often. And so right now, our goal is to figure out the best weights for this model. So we want to make our hypothesis fit our data really well. So quick question for you guys. This is pretty subjective. So if you guys don't get like what we thought of, it's okay. In hindsight, I probably should have made a more objective question, but the question is rank these 4 features and how much they might affect midterm scores. First option is hours spent studying for the exam. Second option is number of classes spent being taken. Third option is number of pets the student has. And fourth option is hours of sleep night before. So yeah, rank those 4. Important to note that negative correlations also matter here. So like if like one of these correlate negatively, put that at like the bottom because it correlates negatively, I guess. So like we're looking at like we're not looking at magnitude, we're looking at like yeah, like sign. It's like sign matters as well, I guess, in the best way to phrase it. Yeah, put that in the chat, or if you want, say it out loud. But I don't know. All right, so I see Maxwell and Noah are agreeing on this thing, on this. Ooh, we have 3 responses. Nice. Hours spent studying, sleep, pets, classes taken. Ooh, okay. So I see 2 choices here. I think Eva and Jonah have the same thing. So the 2 choices I've seen so far, I think Maxwell realizes something here with differences, is that so far the first 2 are in the same for both choices. The first 2 are hours spent studying and hours spent sleeping, which I would agree for, because like that has a pretty high positive correlation. But the next 2 are actually, I would say, the difference. So Maxwell and Noah said number of classes third, pets last, and Jonah and Eva said pets then number of classes. So yeah, I would say Jonah like added a reason to, and I would actually agree with that. And yeah, Maxwell realizes like the main difference is that pets to be next, because okay, this is subjective. So maybe you don't like you think your pets are going to make you study worse for the exam, but I would say all your pets won't help you too much for your exam. They won't hurt you as much as like taking like 10 classes. So this is subjective. So if you thought that this is different for you, I would accept that. But what I was going for here was that your pets will like maybe like give you some mental support, but the main thing is that they won't super help you for studying for the exam. And so their correlation is a lot less to your score. So it'll have like a low weight. But the important thing here with the negative correlation is that number of classes taken actually negatively correlates with midterm score. So the important thing is that maybe this is different for you guys, but for me at least, I would think that if you take 10 classes, you're probably going to do worse than the midterm if you took 3 classes. So because of that, number of classes is a negative correlation. So more classes means worse score. And so as a result, we'll have classes being taken last. It'll be like the, I guess, the least effect on like negative, like yeah, like the question is badly phrased, also a bit subjective, but does that make sense to everybody? Why this ordering is being used? Yeah, cool. If it doesn't, feel free to ask a question. Cool. Awesome. Yeah, I think because you guys have the idea down, which is important, and so that's really good. All right, I think this is Jensen's part, so pass it on to him.
Yeah. All right, so I feel like no one really ever gets excited talking about math, except for maybe 3 blue, 1 brown. But trust me, going through all this math is going to be worth it once we get into gradient descent, which is probably one of the most important and foundational algorithms in machine learning. And if there's one thing that I hope you would take away from beginner track, it's how gradient descent works. All right, so let's get into the math. All right, derivatives. So you probably learned about derivatives in your calc class, but let's do a quick refresher anyway, just to make sure everyone's on the same page. So what is a derivative? So you can think of the derivative of a function as sort of the rate of change of that function, or alternatively, the slope. So if this red parabola here describes the position of a car, then this green tangent line would be the velocity of that car at a certain time. Let's say, I guess, t equals 2. And so notice how if the derivative is positive, then the function is increasing. And similarly, if the derivative is negative, then the function is decreasing. So in other words, the derivative sort of points in whichever direction that f is increasing in. So I want you to hold this thought because we'll revisit this in later slides. All right, so I guess the notion of derivatives also applies to higher dimensions, but instead of derivatives, we have partial derivatives. So take the partial derivative of a function with respect to, I guess, a variable. We treat all the other variables as constant and just take the derivative as you would for a single variable function. So for example, if we're trying to take the derivative of f, which takes in 2 inputs, x and y. So if we're trying to take the partial derivative of f with respect to x, then we assume y to be constant and just take the derivative normally. So let's go through this, I guess, simple example here. So if f is equals to 2x plus 3y squared, then del f del x would be 2 because you treat the 3y squared as a constant and just take the derivative of the 2x. And similarly, del f del y is 6y because you treat the 2x as a constant and take the derivative of 3y squared. So yeah, this is what I just discussed earlier. All right, any questions? Yeah, I have a lot of respect for 3 blue 1 brown because like he actually makes math like really interesting. And I think he also does like a series on neural nets, which I would highly recommend you checking it out. But, all right, just to, I guess just for some background, like 3 blue 1 brown did not sponsor this workshop, so. Oh, okay. You don't have to worry about who 3 blue 1 brown is if you don't know him. All right, let's move on. So I guess a concept that's closely related to the partial derivative is the gradient of a function. So gradient of a function is a vector that contains, I guess, the partial derivative of that function with respect to each of its input variables. So for example, if f takes in n variables, then the gradient would be an n-dimensional vector. All right, so let's go through like a slightly more complicated example. So if f takes in 3 inputs, x, y, and z, and is equal to x sine y plus 2z cubed, then the first element in our gradient would be sine y, because we're taking the partial derivative of f with respect to x. And the second element would be x cosine y, because we're taking the derivative of f with respect to y. And the last term would be 6z squared, because we're taking the partial derivative of f with respect to z. So let's see, there are some activities in the chat. All right, never mind. Okay, so I guess, do you guys have any questions with regards to like partial derivatives or gradients before we jump into, I guess, poll? Hopefully that was clear. All right, if not, I'm just gonna launch the poll. Give me 1 second. I guess I'll give you guys like maybe like 30 more seconds. All right, so f takes in 3 inputs. So that means the gradients should be a vector of 3 elements. All right, I think I'm just gonna end the poll. And hopefully everyone can see the results. So everyone picked the right answer, so that is good. All right. I guess I'll move on to the next slide if no one has any questions. All right. So loss function. So in order to optimize our weights, we first have to introduce this notion of a loss function or cost function. So these two terms are kind of used interchangeably for the most part. So the loss function is a function that quantifies the error in your predictions compared to the target values. And there are, in general, like many different choices of function that you could have picked, I guess, as your loss function. But I guess for linear regression, we'll just go with mean squared error, because that is one of the more popular choices for regression in general. And our loss function looks something like this. So as the name suggests, we're first taking the difference of y and y hat. So y is the actual target value and y has the predicted value. So you can kind of think of this difference as your error. And then we're going to be squaring this error to make sure that it's always positive. And lastly, we're summing this error across we're not summing, we're taking the average of this error across our entire data set. So hence the name mean square error. And also, I guess the subscript here just means that this is on the ith training example. So this is like, I guess, yeah, so y here is just a scalar. Or y sub I should say. All right. So I guess a useful concept to introduce is you can actually think of our loss function as a function of weights and bias, the weights and bias of our model. So why is this true? So our loss function depends on our predictions, y hat, which you can see down here. So L takes in all the y hats. And our predictions or our hypothesis depends on the weights and bias of our model. So here's our hypothesis again, just as a refresher. And so the loss function could also be think of as a function of weights and bias of our model. So you can convince yourself by, I guess, imagining that you're substituting the y hat or our hypothesis into our loss function. So what you end up with is a bunch of W and B's. Although it would be a little bit messy. But okay, so this might seem a little bit like trivial right now, but I guess understanding the idea that the loss function can be expressed as like a function of the weights and bias of our model is pretty important for understanding how gradient descent works, which we'll get into in, I think, a few slides. I think. No promise though. Okay. But we'll get there eventually. Okay, so we have another poll. So I'm gonna pause here for some questions before we, I guess, get into the poll. All right, I guess let me just launch the poll for now. If you have any questions, feel free to, I guess, type in chat. I'll give it like, I guess, like a minute or so. All right, so everyone picked A, which is the correct answer. Oh wait, I'm not showing the results. Whoops. Okay, so everyone picked A. That's the correct answer. So like I mentioned, the loss function sort of quantifies the error of the predictions that your model makes compared to the true value. Okay. All right. Okay. So as I guess discussed earlier, our loss function is basically a function of the weights and bias of your model. And our model learns the underlying pattern of the data set or the training data set by updating its weights and biases. So if the loss function outputs a small value, that means the error is small. And in other words, the model is accurate. So the crux of the problem, at least for linear regression, and actually for, I think, most machine learning problems, is just to find those weights, find the set of weights that minimizes the loss function. Okay, so how do we do that? Any ideas? Preferably without looking at the next slide. Loop through a ton of values. Yeah, I guess sort of, but there's I guess we're doing like in slightly more intense manner. Like, I guess force. The thing about it, like each weight and bias is technically like a real number. So they're like infinite number of like real numbers you could have like I guess, try and calculate loss and find minimum. I guess that's technically true, but that's, I guess, not really, it's not really like touching on the main point. Okay, someone said find derivative and critical points. Okay, that's actually a very interesting comment, because like, I guess at least for linear regression, there is like an analytical solution, but we're not going to be covering the closed form solution in this workshop. We're going to take a slightly different approach, which is gradient descent, as you probably expected. All right, so let's formalize what we discussed earlier about derivatives. So let's assume here f is a function of one variable, and f prime in this case is the derivative, which indicates whether a function is increasing or decreasing. I think we discussed that in a lot of detail in one of our earlier slides. So basically, if f prime is positive, then the function is increasing. So if you look at this graph here, if f prime is positive, which is, I guess, in this region here, then f is increasing. So what does it mean for f to be increasing? So that basically means if x increases, then f also increases. So yeah, if x increases, then we're following this parabola, and we will also increase. And so I guess because we're doing gradient descent as opposed to gradient ascent, we want to decrease f. So what we have to do if we're in this region is to actually go left or in the negative x direction to decrease f. So we have to subtract something from x. So, and similarly, if f prime is negative, that means we're in this other region here. Then we want to decrease f, or in order to decrease f, we have to increase x. So I have to go to the right if we're in this negative region. All right. So I guess to formalize what I just said, so if we want to minimize f, so if f prime is positive, then we want to subtract from x. And if f prime is negative, then we want to add 2x. So how can we do that? The answer is use f prime itself. This is like a 300 IQ answer. But I guess something that you have to keep in mind is we want to do the opposite of f prime tells us to, because remember, f prime points in whichever direction that our function is increasing. So if we want to decrease our function, then we want to do the opposite of what f prime tells us. So we can update x like this by subtracting some constant times the, I guess, the f prime. So this alpha is actually a pretty important constant, and it actually has a name. It's called the learning rate. So you can kind of think of the learning rate as like the step size that you're taking like every iteration of your gradient descent algorithm. So if you're taking a big step every time, then I think you'll probably get to a like minimum like pretty quickly, but then you might also overshoot. And if your step size is like really small, then it'll take you forever, but you'll get there eventually. So yeah, I guess if there are any questions, I can take them. Let's see, there's something in chat. Oh yeah. I guess that's a pretty good answer from Nikhil. But like, if not, we're just gonna jump into this, check out this cool visualizer to see how gradient descent works. All right, so let's start with this relatively simple function. It's a parabola. So let me set this up. So as you can see, like, because I guess the slope here is positive, so we're going in the negative x direction. And then we do this like over and over again, we'll converge at the, I guess, the minimum, which in this case is the optimal solution. Okay, so what happens if I guess, decrease the learning rate by a lot? So you'll notice that it kind of takes forever now because the learning rate is so small, but like it will get there eventually. This just takes a while. Okay, I'm not gonna go through I'm not gonna keep clicking. But like what happens, all right, so now you might be tempted to say like, why don't you just pick a bigger learning rate? All right, so let me try that. Let me zoom out a little bit as well. So we pick a learning rate that is like too big. We end up like not converging at all. So in this case, we're just like oscillating because this is like a very special value for this function. So we're just oscillating. But then if we increase this like by a little bit more, then what ends up happening is we're actually diverging from the minimum. So the bad things will happen if you're diverging. So namely like Python will probably give you like an overflow exception of some sort. So this is bad. So you want to avoid this case at all costs. Okay, but the learning rate actually does not have to stay constant at all over the course of training. In fact, I think most optimizers that people are using nowadays, like ACM, actually like uses like an adaptive learning rate approach, but that's like beyond the scope of beginner, so we're not gonna cover adaptive learning rate. But if you're interested in how that works, like I would encourage you to, I guess, just like maybe like Google it, and there are some like pretty interesting articles. Okay, let's go back to our slides. I guess I can also take some questions. Oh wait, if there are any. All right, if not, let's, oh wait, there is a question. So we're doing single variable gradient descent on the loss function. All right, so not quite, but like the single variable case is just for, I guess, demonstration. So I guess let's sit back for a second and like just think about how gradient descent actually works at a higher level. So I guess you can kind of think of like gradient descent as like a ball that is rolling down a hill. And you can sort of think of the learning rate as the momentum that the ball carries. So if the ball has a lot of momentum, then it'll get to the valley like really quickly, but it might also overshoot. But if the ball has like very little momentum, then it'll sort of get there eventually, but it'll just take a while. So I guess the idea here is just, oh, okay, never mind. I was distracted by chat. Okay. So I guess like picking the learning rate in general is a pretty hard problem, but which would require like, I guess, a lot of time. And like, there's actually like a, I guess, a technique called a hyperparameter tuning. But like, I guess with like adaptive learning rate approaches, it's not as important. And certainly not for linear regression because, okay, wait. I guess, okay, forgot what I just said. Okay, so let's actually think about how the loss function can be represented. So if this curve here is our loss function, then the x-axis here would be the weight, and the y-axis might be the bias. If our model only has like one weight and one bias, and this z-axis here would be our loss. So if we choose like a certain weight and bias, then our loss might be like really high. So we're in this region. So like, but if our weights and bias are like, I guess, around here, then our loss will be like really low, and that is where we want to go. So in general, by computing like the derivative with respect to the weights and bias, we can sort of figure out how we should adjust our weights and bias. And that would let us know like that would give us sort of an idea of what the optimal weight and bias should be. And also you can notice like the difference between the function on the left and the function on the right. So the function of the left is like, looks really simple, and it's really easy for gradient descent to optimize because there's only like one, I guess, local minimum. So this is what is known as the convex function. So what that means is there's only one minimum. And this is also sort of how the loss function for linear regression looks like. Whereas this function here has a lot of like, I guess, bumps. And so this is in general like a much harder like function for gradient descent to optimize. But if you're training like a more complex model, like a neural network, then this is what your loss function will look like in general. So it's much harder to optimize with gradient descent, but I guess that's like its own topic. So, and I think we'll cover that in more depth in advanced track. So, all right. So that was a lot of stuff to take in. So if you guys have any questions, please let me know. I guess if not, I'll try to like, I guess, give you guys a perspective on why gradient descent works in a more like through a more mathematical lens. So remember our example earlier where like in our one-dimensional example, the derivative always points in the whichever direction f is increasing. So if you think about it, the gradient is basically just a vector of partial derivatives. And if each of these partial derivatives points in the direction that f is increasing in its, I guess, dimension, then taking all of these as a whole, the gradient should also roughly points in the direction that in which f is increasing. And by subtracting the gradient from, I guess, our x vector, then we can actually like, you can easily see how that would like cause our function to decrease because we're okay. So to formalize what I discussed, so in multivariable gradient descent, the gradient points in the direction of steepest ascent. So that was kind of like what I was trying to like get at earlier. That means if we go in the same direction, we would increase the value of the function, but that's the exact opposite of what we want to do. So we want to go in the opposite direction, hence gradient descent as opposed to gradient ascent. All right. So instead of x being like a scalar, x is now a vector with n values. So f takes in n inputs as well. So the gradient of f is also a vector with, I guess, n elements. And we can update, I guess, our x using the gradient update rule, like so. And alpha here is our learning rate, which we spent a little bit of time discussing earlier. All right, I think we have a question. So it's a long one. So multiplying the gradient by a single learning rate means each partial derivative is being multiplied by one learning rate. Why is it acceptable to do that instead of using a separate learning rate for each partial derivative function? Okay, so that's just an excellent question. So in general, if you're using a fixed learning rate, it is generally the case that you'll use like one learning rate for everything, just for simplicity. But if you want to use like an adaptive learning rate approach like ADAM and like RMS pros, like usually the learning rate is also a vector, because if you use an adaptive learning rate approach, then you sort of want like each weight to have its own learning rate, if that makes sense. But that's a very good observation. But like, I guess for now, we're just assuming the learning rate as a scalar just for simplicity. But yeah, that's a pretty good question. All right, any more questions? Okay, if not, let's move on. So this is what the gradient of our loss function looks like with respect to the weights and bias of our model. And now that we have the gradients, we can update our weights and bias like this. So this is really similar to this gradient update formula that we have. So one thing that you should notice here is, in order to update the weights and bias of our model like once, we have to go through our entire data set. So this is not the most efficient. And in fact, you see that like a lot of variants of gradient descent are, I guess, developed to tackle this inefficiency, like I guess SGD. But I guess if you don't know what SGD is, I don't worry too much about it. All right, so let's see. So I can actually try to go through a math if like there are enough interest. So let me try to launch a poll to see how much interest. Okay. All right, so if you want to go see like how to derive this, then click yes. If not, then click no. So we also have the full derivation of the gradients down here, but it is slightly more complicated. Or, I mean, it's basically like the same thing, but like the notations are slightly different than what we have in our slides. Okay, it seems like we do have some interest. Okay, so let me go to my iPad. All right, give me 1 second. I guess. Let me stop sharing screen. All right, I think you should be able to see my iPad. All right, so let's get started. All right, so let's go through, I guess, a more simple case where we only have one sample in our data. And we have n features. All right, so X here is a row vector with n elements. And remember, Y is just our target, so Y is a scalar. And I guess the weight here would be a column vector with n elements. And the bias term here is also a scalar. Okay, so now that we have defined or gone through all the setup parts, then we can finally define our hypothesis. So our hypothesis takes in the input vector, and it looks something like this. Okay, so now we can, I guess, define our loss, which is just y minus y hat squared. So because we have only one sample in our data, we don't have to include the summation symbol. And now we can start taking the derivative with respect to our weights, or one of our weights. Let me just say like w sub j. All right, so del L del w sub j is going to be, let's see, 2y minus y hat. And then now we have to apply the chain rule. So y is just a constant in this case, so we can just ignore it. But notice y hat up here is a function of our weights and biases. So we have to apply the chain rule. So we have this term here, del y hat and del w sub j. All right, now we have to figure out what del y hat and del w sub j is from this equation up here. So notice how w sub 1 is multiplied by x sub 1, w sub 2 is multiplied by x sub 2, and w sub n is multiplied by x sub n. So del y hat del w sub j here is just x sub j. And I guess similarly, del y hat del b is just going to be 1 because the b here is isolated. And now can finally actually evaluate what del L del W sub j is, which, let's see. So it's gonna be, I guess, y hat minus y and x sub j, because I'm putting this minus sign here. And similarly, if you do this for del L del b, then you'll get 2 times y hat minus y. Okay. All right, so any questions? All right, so this is just for y is at x sub ij. Okay, so the reason that's x sub ij, because in the slides we assume we have like more than one sample, but like now we're assuming there's only one sample, so I dropped the I subscript. But like in general, if you have more than one sample, the derivation should be like really similar. So I'm not gonna cover this in the workshop, but like if you're interested, you can check out the full derivation that we have. And I think the full derivation also covers the closed form solution. So if that's something that you're interested in, then I would encourage you to check that out. Okay, back to the slides. All right. So I guess minimizing the loss function in this case can be thought as just figure out what the best fit curve should be for our training data. And the best fit curve in this case is the optimal solution. So if we look at this, I guess, animation down here, so this linear regression with only like one feature. And when we're minimizing the loss, what we're actually doing is we're trying to fit this line in through our data. So these two things are equivalent. And the good news is you'll implement this from scratch in one of our guided projects later in the quarter. So yeah, you'll definitely get a lot more familiar with all of this stuff. Yes, and we'll be using NumPy primarily to do so. All right. So after we learn the optimal sets of weights for our model, then we have to evaluate how well our model do on data that it hasn't seen before. So to test our model, we first have to select some data that we have that are not being trained on. So in this case, it's just a test set. And then we feed the input features into our model. And obviously we keep aside the true y true y values in maybe like an array of some sort. And then our model would generate the predictions using the hypothesis and the weights that we learned. And then we can calculate the loss between our predictions and the true y values. And that loss sort of tells us like how well our model has performed. So in general, your testing loss is going to be higher than your training loss because you haven't been directly trained on the test data. But the goal here is actually to minimize the testing loss because that is a more accurate representation of like real world data. All right, so I guess that's it for all the math. I hope you guys enjoyed all the math. I know it was a lot to take in, but hopefully you learned something. All right, so I'm gonna actually hand it back to Nikhil now, who's gonna go through the coding exercise that we prepared.
Yep, let me share screen again. Okay, cool. Let me open chat too so I can see that. All right. How many people do we have today? Nice, we have 6. Okay. So I guess first thing I'll ask is that, so we have the code lab. You guys can go ahead and open it. One thing I wanted to ask from last time was that last time we had all of us follow along, all of us followed like Jensen as he went through it. So I was trying to quick poll. I wanted to see if you guys would like to do that same thing again, where we all sit in the same room, or if you guys would rather do breakout rooms where me and Jensen have our own room, and then basically we split 3 and 3, and we have like a smaller group, so it'd be maybe easier to ask questions and things. So I just want to see, would you guys prefer doing this all in the big room or having 2 breakout rooms where we go into it in smaller groups? So yeah, launch the poll for that. Just want to see what you guys think. For you guys, like 15 more seconds. But it seems pretty clear to me, at least so far. But let's see. Okay. Okay. So let's end the poll. And we see, okay, yeah, you guys want to stick in the main room. So let's go ahead. Oh, I didn't share the results. So yeah, you guys stick in the main room. So we'll stick with that. And yeah, let's do that. All right. Give me 1 second. Gotta. Sorry about that. My dog came in, opened the door, and then left with the door open. So did not want any distractions. All right. So hopefully you guys are following along with me. Did the link work for everyone? I just want to make sure to link that link, like no one got like locked out of the notebook. Just like, okay, cool. Thumbs up. It worked. Awesome. Great. So you're all here. So first thing we're doing is we're importing a bunch of things. So first thing is NumPy. We'll go over NumPy in a bit more detail in a later workshop, but for now, just note that this is like a really important library for like matrices. Then we have scikit-learn, or sklearn as it's called in Python. And this is just a relatively useful general purpose machine learning library. We did it a bit last week, but we'll try to go a bit slower about sklearn this week because it was a bit confusing to some people. So keep that in mind. The big things here is that we're importing data sets. So later on in the workshop, we'll be looking at a data set for diabetes, and we'll be using that later on. We're also importing sklearn's linear regression model. So that's pretty important. It does it for us. So it's kind of nice. We're importing everyone's favorite function called train test split. We worked with this last time. And we'll go into it a bit more again. Hopefully you guys remember what it was last time. But if not, we'll go over it again. And the last thing is we'll have some metrics, or second last thing is we have some metrics. So R2 You guys probably know what it is. The coefficient like relatedness or something, some coefficient that determines how well your data is fit or how well your fit is. And mean squared error, which we talked about earlier. So like you take your error, you square it, and you take the average of it. And then last thing is matplotlib.pyplot. This is just for plotting libraries. So if you want to plot our graphs, it's nice for that. So let's go ahead and run that. Yeah, it's okay if it's not authored by Google. It's authored by me. So me and Jensen made this. So you guys can trust us. Yeah, it should work. Keep in mind these two functions for later, but I can keep in mind all of them, but these two are like helpful for things. All right, so next thing is data creation. So luckily for you guys, I've gone ahead and created an epic data set for you guys that's handmade. So it's pretty awesome. Go ahead and run it while I dive through what it is exactly. And so what we're doing here is that we're creating 300 data points between 0 and 50, evenly spaced. So this is what linspace does. Don't worry exactly what it does, but just remember that we have 300 data points between 0 and 50. And then we're going to add some noise to it. So like just like making it more varied, so it's not like a straight line anymore. And then we're gonna have noise, and what we're gonna do is we're gonna create a y that's like 4 times all these x values plus 14, and then plus our noise. So we would expect without the noise we have like a y equals 4x plus 14, but we have noise now, so I don't like that happens. Okay, we're back. So because we have noise in this case, we're not going to have an exact 4x plus 14, but it'll be pretty close to that relationship. And so that's our data. We'll see it in a second, but first we need to run our awesome function called train test split. Hopefully you guys remember this. Yeah, Denton said make a copy, or yeah, make a copy to drive if you want to run your stuff on it. We recommend. So our first function we need to run is train test split. So this is up to you guys. So take a minute to think about this. Luckily, I've copied the docs for you guys, so let's go ahead and look at that. But this function, what it does is that it splits arrays and matrices into train and test subsets. So remember how we were talking about how we need to train in our training data, and then based on that training, we need to test it on a certain subset of our data. This is what that model does for us. So we have our big data set of X and our target data set of Y, and we want to split it into X train, X test, Y train, and Y test using train test split. And now the question for you guys is, okay, what do we pass in and what are the arguments for this case? We did this a little bit last time, but we recommend looking through these things, these parameters on the website, because they give you a pretty good detail what's happening. We don't need all of them because some of them have defaults, but occasionally we want to override the defaults. So that's important to notice as well. So I'll give everyone 1 minute to think about it because most of it's here, and then I'll ask you, or if you have it earlier than that, feel free to write your inputs in chat. Okay. I'll give everyone 30 more seconds. I see your answer, Maxwell. But I'll give everyone like 30 more seconds to think about it as well. Yeah, I'd recommend actually, because it's a bit early, to either have a test size or a train size defined. Yeah, not both, but one of them, because you might not want 0.5 or 2.5, because that's really small. Yeah, it's not bad, but it depends. I think it's been 30 seconds though, so, or like a minute or so. But so if you guys have any answers, go ahead and put them in chat. If this is confusing, just ask questions, because I know there's gonna be a lot of things to look at one time. So if it doesn't make sense, ask a question in chat, or maybe PM me or Jensen. We can answer your question if you don't want. That would make it a lot easier. But yeah, go ahead and put your answers in chat. And so first thing to see is what Maxwell put is x comma y, and I do agree with this. Another thing I'll actually have here is test size. I just like 0.2 because that means that a 50-year data set is in your testing data set. Okay. Yeah. Sorry, guys, 1 second. Yeah. Okay, so sorry about that quick thing, but we have our data set, we have our things. We're now splitting the data set into 4 parts. So we had our X data, which is like all of the, I guess like the inputs, which is one-dimensional inputs. So like 1 to 50 are the inputs. And we have our Y, which are our labels. So our target. So like let's say like this would be like a Y with mx plus b equation. So that's that case. And just to reiterate, train test split is splitting X and Y in 2 parts each, so that we're splitting X into X train and X test. So what we're going to do actually is we're going to make our model only learn on the X train data, and then we're going to test the accuracy on X test. And so again, we're going to train on only Y train, and we're going to test on Y test. So these are the 4 variables. And this is returned from train test split. So as you guys can see, it returns a list of length 2 times length of arrays. So since we passed in 2 arrays, it's going to return 4 arrays because 2 times 2 is 4. Again, parameters are things we pass into a function. So this function takes in many parameters. So it takes in a number of arrays. So in this case, our arrays are X and Y, because X is an array of 300 data points, and Y is as well, because Y is just 4 times that plus 14 plus noise. So what this means exactly is that this is basically taking every value in X, multiplying it by 4, adding 14 to each of them, and then adding a noise value to each of them. So this is also a 300 length array. And so what we're doing is we're actually going to split this data set into certain size. So you can see these two parameters here, test size and train size. And so they're kind of complementary, as you guys can see from if you guys read these descriptions. Basically what this is that this is basically a decimal between 0 and 1 of how much of the data set should be in the test split. So in our case, I went and put test size equals 0.2, which means that I want 1/5 of the data to be in X test and 4/5 to be in X train. And same for Y test, Y train, and Y test. So most of the data will be in X train, which is typically how we do it, because we want to train most of the data and then test them a little bit, because we want to train it on as much as possible, basically. And so that's how we got these arguments. And so X is the first array we want to split. We want to split Y the same way. And we want to test size equals 0.2. An important thing to notice is that random state, we're not going to care about too much, because if you want to keep your data consistent, like this is important. But this mostly applies to this thing called shuffling. And so it's important. The default for this variable is true. So what that means is that if we don't specify the value for that, it's going to say it's going to be equal to true, which is good because we want shuffle data. Because shuffling data basically means that usually what this model does, this function, it takes the test size is 0.2, right? So it takes the last 1/5 of X and makes that X test. It takes the first 4/5, the first 80% of X, and makes it what do you call it? X train. And so it's important to shuffle our data in this case, because actually I'll just show you guys. Oh, wait. I'll show you guys in a second. So in my case, I'm going to put shuffle equals false. You guys shouldn't do this, but you'll see the difference between shuffle equals false and shuffle equals true. But just a reminder, don't do shuffle equals false, because we don't want this, but it's important to notice what would happen otherwise, because your data won't be mixed up, basically, is the most important part. And this is important because this data is ordered, so it's important to notice that. Okay. Does that make sense to everybody? Hopefully you guys all have this like this, something like this. This isn't required because this is the default value for that variable, but these first three are recommended. And these first two are required. But the general purpose of this function is that it's splitting x and y into subsections so that we can test on, we can train on parts of it and test on other parts of it. Is that good for everyone? I guess a better question, any questions, because maybe it's not good to everyone. Yeah, I would say we'll see what's up. I don't think you should have stuff for those laws, but just run this. We will see the difference, I think. But yeah. Okay. If there's no questions, feel free to ask questions, but if there's no questions, let's go ahead and move on to visualizing the data. So what we're going to do is we're actually going to plot the data using plt.scatter. So this is a scatter plot, basically. And so this is a two lines of code that we're going to do. And we're going to plot our data. And so as you guys can see, it's going to be, I'll give you a hint, we're going to have to do two of these plot.scatters. And I guess important to know is that if you do this, like if you type the function in, the notebook will give you the parameters as well. I like to see it here as well because it's more useful. But the important thing here is that there's parameters, so two arrays, x and y. S is I guess an optional parameter, so I won't worry about this. But the most important thing is x and y. So I'll give x and y are familiar variables to us. So I'll give you that should help you determine what we should pass into these two. So we want to plot. I guess importantly, we want to plot x train and x. We want to plot the training and testing data sets separately. So I'll give you all like let's say we're actually like not the best of time, so I'll give you guys 30 seconds or so to think about this. And if you have questions, feel free to ask again, because I'm not sure if this is too fast or too slow. So yeah. But hopefully the parameters make sense in this case. The parameters we're passing in the scatter are x and y, which we see, we should already see. X train, y train, x test, y test. But yeah. Once you have an idea what it is, write it out in chat. Okay. Awesome. So yeah, Maxwell got the two answers. Hopefully that makes sense to everyone. If it doesn't, please, yeah, either PM me or Jensen or ask it in chat. But this is the correct response. What it is x test, comma y test, and x train, comma y train. What I'm also going to do actually, just for making it more clear, is actually set a color to like red and set a color to blue. This way, these are just parameters that we can take in the function. Maybe it'll show it here. Color. Yeah, colors. So there's a lot of colors that we can set to be, but you'll see the color appear here. Don't worry too much about it, but it just lets us see the color better. And so if we run this, we'll see. So if shuffle equals false, we'll see this. You guys probably see something different though. You guys probably don't see red all at the end. You probably see red everywhere. And so if it goes true, you'll see red you see red spread out everywhere. And so I recommend having shuffle equals true. Like I think technically false is okay, but you don't want like a big outlier, like a big chunk of data to not be in your training set. So in the old example, like all values above like 45 weren't in the model. And so that can make the model a bit less accurate on like higher values, for example. So it's good to have your training set also be pretty spread out, but it's not required, but I recommend it. But yeah, this looks pretty cool. And so that's why we're visualizing it for that reason. It looks pretty cool. And you can really see what's happening now. But yeah, this is our data. This is our X and this is our Y. Any questions about that? If not, let's move on. But if you have any questions, feel free to ask later on as well. This one went to fitting the model. So we gave you the model object itself. So we made a variable called model, and it's a linear regression object. So now we have a thing called model. And now what we want to do is basically call a function on the model to fit the data. And so what I'm going to do is open up the model from sklearn, linear regression model from sklearn. And we already created it for you guys, so don't look at it here, because this is already done for you, because like this class instantiation, that was done here. So don't worry about that. The important thing is to think about is, this is important later, but important things are the methods. So methods are things you can call on the model to get certain values out of it. So for example, we have fit, get parameters, predict, score, or get parameters. So basically what you can do is let's say you wanted to run model.score, right? You wanted to run score. You could say model.score, and that would run the score method. And so the question here is, with these docs, which function do we want to run out of these 5 functions that we have to fit our data set to get a fit for our parameters, or like our linear regression? Just the function name is fine for now. We'll dive into the exact parameters. Cool. We'll give everyone like 5-10 more seconds, because hopefully there's only 5 choices. Everyone understands, but if not, just ask, because I guess I can't really help you if you don't ask. So yeah. Nice, yeah. I like how Julian worded it. I think fit fits. Yeah, that's really good wording. Yeah, you guys are right. So it is fit. So we want to run model.fit, but we'll see. We don't see it here. We'll see here that fit takes in parameters as well. So it takes in X, a Y, and a sample weight. This is optional though, and so we're not going to care about this. But the important thing is what do we pass into X and Y. Hopefully this is similar to what we did before, so, and it should make sense. But write it in chat, so I know you guys all got it. Also, it says, yeah, training data, target values for training data. So that should also be a cool hint. You tried X train, Y train, got an error. That is important to know. Yeah. Yeah, I'll get to that in a second. Yeah, you are right that you should get an error here, but that is because I in fact forgot to type in something earlier. But let's see what happens, because you're right that we want to pass in X train and Y train. But as Maxwell said, there is an error right this way right now. So we run this, and so we'll see. What we'll see is that we'll get like a huge error, which is like really ugly. But like errors are important in programming because we're going to get them a lot. But the important thing is that we see here is that like expected 2D array, the error is expected 2D array got 1D array instead. And it says either reset your data using this or something else, right? So the important thing here is that if we go up above and let's say we add like a line above, let's see, we type in xtrain.shape, and this will basically tell us the dimensions of the array. And we see here that xtrain is a 240. It's like a 240 array, like the array of like size 240. So this is one dimensional. And the problem here is that fit takes in only 2D arrays. So luckily enough, the code here tells you how to fix that, is that you call reshape -1, 1. And so what we actually do is that above this, we want to run x train equals x train dot reshape -1, 1, and same for x test. And so what this does is basically it changes the shape of x. Actually, I'll do this like in a different code block because that'll make it easier. Let me add a code block below. So we do this, right? And so now what we'll see is we call x train dot shape after this. Before it was 240 by 240, right? It's like a one-dimensional array. Now it's 240 by 1. So if you actually print it out, I think that may be easier to see. Like now it's like a big column, a big row vector, or yeah, this is a column vector. Yeah, I say row vector, a big row vector. But the important part is that now it's a two-dimensional array. And so that allows it to be accepted into the next function. So reshape, what reshape does is basically it takes our data and changes the dimensions to fit what we inputted. So what this means right here, -1, 1, means that we're basically saying the second dimension has to be 1. And then the first dimension can be whatever it needs to be to fit this. So because this is 240, if we reshape this to have a 1 in the second place, we need to have 240 up front. That makes sense. So if we had a 2 here instead, this would be like a, what do you call it, like 120, for example. Basically, it does the fit. But the important part is that we're basically changing, we're like adding an extra dimension to our data set to help it be fitted. I wouldn't worry too much about what that is, but the important part is that fit only takes in two-dimensional arrays, which is why we need to do this reshaping. Any questions about that? A nice find, Maxwell. That's important to find. Okay, cool. If there's no questions, let's move on to printing the parameters. So we fit our model, and we expect to have like a y equals mx plus b equation, right? So we expect to have one weight and one bias. And so what we want to do is print out from the model those two parameters. So we want to like print like parameter 1 and print parameter 2. It's like, I'll just say like print coefficients and print bias. Oops, can't do it. And if you guys are having a question about the notation, what this does basically is that coefficients, and there's going to be a colon, it's going to be a space, and then these brackets are going to be replaced with whatever's in the format thing. So whatever I pass into this method will be printed out here. Whatever's passed in here, we print it out there. I guess that works. But going back to the code, now that we have we fit our model, we want to look at the attributes of our model. So our model is going to store like the best fit for our model, like what the variables are. It's gonna save our weight and our bias. So we want to figure that out now. So let's see. We already talked about parameters earlier. So let's talk about attributes. So maybe you guys can notice here what the important attributes are to get the proper things. So there's 4 of them. We need 2. Hopefully the names make sense to you guys. And maybe if you guys read it, it'll make extra sense to you what this is. But the question is, what do we print out here? I guess that is model about something. Also, this tells you a bunch of options. So Maxwell says model.coefficients. I agree with that one. What about the bias? It's also an attribute here. So you have 3 choices left. One of these 3 has to be the bias. Intercept? Nice. Yeah, it is intercept. Yeah, if you guys, I guess this comes from like slope form, but basically like slope intercept forms. So like intercept is like going to be the bias. It's going to be like the plus b, and this is going to be like the m, like the weights. So I equal this would be. So if we run this, we're going to get our coefficients and bias. So we see our coefficient is 3.98. So our slope is 3.98, and our bias is 14.24. So like our intercept is like 14, like about like here or something, like 14.24. So our line's going to be like this or something, like that. Cool. Great. So that's awesome. Any questions about that? How time we have? We have 20 minutes. Okay. Let's try to. If you have any questions, just write them in chat. I'll get to them. It's going to move on to the next part, which is writing this on the test data. So we'll get to the check error next, but first part is writing on test data. So we have our fit now. We have our parameters. So the important thing now is we want to test it on our test data set. So again, our model has five methods. So which of these methods do you guys think is going to be the one that we want to use to test on a test data set? Just the name this time again, just to have a name. Score. So yeah, score could be used. It's more of like a determinant R squared. But yeah, let's use predict because we're going to use predict because predict is just going to say like, given a certain x value, what do we think the y is going to be? So let's do that. So now that we have that, let's declare a variable called y prediction. And we're going to set that equal to model dot, where is it? Predict. And so what do we pass in is the question. Now, remember the parameter is an array-like thing. That's an x. Like, what do we pass in to run our to test on our test data set? Yeah, exactly. We're running x test. So x test is all the input variables from our test data set. So we want to pass those into the model. And what the model is going to do is that the model is going to use the coefficients and the bias to make a prediction. So that's going to make a bunch of predictions. So if we print out like ypred, it's gonna have a prediction for each x input. So that's that. So we have that now. Next thing is checking error. So we have two awesome error checking methods above, mean squared error and R score. The next part is finding our mean squared error. So I'm just gonna have it at the beginning for you guys. So let's just say right, MSE equals and R up 2 equals. And so now you guys can figure out, or take like 30 seconds to figure out what we pass into these two. I guess quick notes. All right, you can see that the inputs to R2 score are Y true, Y prediction, and these two are default, so we're not going to worry about them for now. I think the same is for mean square. Yeah, so Y true and Y prediction. So what do we pass in for Y true and Y prediction in this case for these two? It is the same thing, so I'll let you guys know that. For both, it's the same thing for both of these. Not like Y2 is not Y predict, but like yeah. Y and Y predict. Okay. So second one is right. I'm pretty sure I know what you mean by the first one, but I'm going to be a bit stingy here, and I'll say that we only tested on the test data sets. Why we want to pass in the entirety of Y? And why would we want to test? So if we did Y train, we'd be comparing the inputs from X test to the outputs from Y train. So they're not related at all. So instead of Y train, what would we do instead? It's not Y train, it's not Y. Because Y is the whole thing. Y train is only Y train is related to X train. So X test and Y test are not related at all. It's like saying like yeah, took all 3 times. Don't worry about it. It's confusing, but I guess it's a good thing to talk about though. Is that like if we actually looked at you looked at Y train, it'd be like comparing like student two's results to student one's answer, like student one's end goal, which doesn't make sense, right? So yeah. So if this is y-test, and this is also y-test. Let's just print them out too. So yeah, they're kind of discrete values. Like we don't know what MSE really means, like 225, what that really means. But you guys probably know about R squared, because like R squared is like the closer it is to 1, the better your model is. So this is 0.94 about, which is pretty good. So we like that. Okay, so the next thing is plotting the model. So now that we have our coefficients and stuff, we have our prediction, we have like our how bad it is and stuff. Let's try to plot it again. Like let's try to plot our line on top of this. So from back there, we have our plot, our two scatter plots. So we had those two. Now what we want to do is plot our line. So this is a bit complicated and we don't have too much time left. So I'll give you guys the first line of it because I think this is important. But let's say x-axis equals numpy dot linspace. So linspace again is creates an array of evenly spaced numbers. So basically, we're going to start at 0. We're going to stop at 50 because that was our earlier range from before as well. And we're going to have none data points again. And so what we want, the question is, what are our y values going to be? What's our y-axis? Given that we know our coefficients and bias, and how are we going to plot it? Yeah, because I guess plot has the same syntax as scatter, so same thing. I don't think I need to reshape it because we're not running it through the model again, right? Use rank to get the y-axis. Okay, so let's go back to rank and see what it does. So rank is the rank of a matrix of X. I won't go into details about what rank is. If you guys take linear algebra, you'll get to it. But let's say that X is not dense in our case. So we don't have access to this variable. Let's just say that. But it's not rank in this case. It's actually not using the parameters of this. It's actually just using, we're going to use coefficient and intercept are our two things. And it should be similar to how we do the data stuff as well. Like look at how we make y from X in here. And that should help you make y from X in this case as well. Oh, actually, yeah, I guess that's not better. I might have forgotten how I did. Yeah, that is what I was thinking about. I do think that there's many ways to do it. I just remember that I might be able to do model.predict as well. I think I might have shut that down a bit too quick. I think both ways work. So this definitely works as well. But I get what Jitsun was saying earlier. So you have to do 0 here because if you remember from earlier, coefficient was actually an array, so we need to index into it. So what this 0 does here is that instead of having the brackets, we're going to have the number itself. I think it's good to practice to have in general. That get the number in this case times x test plus modulo intercept. This should work, and then we plot those two. So the plot, we don't have much time, so I'll give it to you guys, which is x-axis comma y-axis. This should work. But it did not, so let's figure it out. X-axis instead of x-test. X-axis instead of x-test. Where did I use the wrong one? Oh, yes, I see you guys. Thanks. Yeah, awesome. Thanks for catching that. And it's a lowercase x because, yeah. Good catch, everyone. So yeah, you guys can see, oh, the line color is bad. Let's define the color again. Color equals red. But this, yeah, gives us line of best fit. I think another way to do it, which Jensen just reminded me of, is that we could also do model.predict on x-axis. I think this is also the easier way to do it. I need to do the reshape thing again, which is why it's I'm a bit slower than Jensen. So shout out to Jensen for being on top of this. But you can do x-axis equals reshape, or remember it needs to be a 2D array in this case. So we do x-axis dot reshape -1, 1, and now this should work, where we basically have the x-axis, we predict on the x-axis, we call the prediction function on it, and then we plot it. We did the same thing as applying our coefficients. So both of these ways work. I was being like, I guess, I don't know, I forgot about this way for a second, but both ways work. So don't worry if you got one way or the other. I think this way is generally better for high dimensional things. So I'll use this way in the future, but that's my bad for steering everyone in the wrong way. But, so I'd stick with this if you guys can. But this is it. I guess also a cool feature is if we set something called a label here and set this equal to fit, we can have a legend for this plot. So that's pretty cool. So now we can see our training testing, like our things. So that's pretty cool. But yeah, we just went through a whole linear regression right there. So that's awesome. I know it's 8:50 right now, and this is a pretty long example. So what I'll do is I'll leave this example for you guys to do on your own if you want. It's pretty similar. The big difference here is that we're loading a data set. So look at these dots from data set. I'm also going to use this data set has 10 dimensions. It has 10 inputs. So it's not 2D anymore. So you can't plot it, but instead it's 10 dimensional. So that's pretty cool. But the steps otherwise are pretty much the same. So like load the data, split the data, create the fit, check the parameters, get the prediction test, and check error. So yeah, it's 8:51. So I don't want to start it. So I'll just go back to the slides for now and leave this for you guys. I'll also, yeah, we'll give you guys the solutions like on GitHub. So if you guys follow the GitHub, we'll get into that. But yeah. Oh, if you guys don't know, GitHub's like a way to like host code online. So it's a way to have our code be on the internet. So it's not. Yeah, just wrapping up real quick. What we just did is called supervised learning. So basically what we did is that we gave our data, our model data. We gave our data model. We gave our model data. And what we did basically, we said is that we're going to give you the inputs. So we're going to give you like the number of hours studied, the number of times spent procrastinating. We're also going to give you how the student did. So we're going to tell the computer that student 1 who studied for 1 hour and was at the beach for 100 hours got like a 5%. And so now it knows how to predict well. So after a bunch of data like that, it's gonna basically learn like a best fit for our case. And so there's many types. This is just one type of or of supervised learning, but there's many types of supervised learning. One thing is called classification. So basically figuring out is something in one class or another. Like is something like a dog or a cat? Is something like a UCLA student or a USC student or something like that. Those type of things. There's regression. We just did regression, so that's like mapping like certain number inputs to other number inputs. And so it's important to think about when you want to do supervised learning. Do you want to classify something or do a regression for like this type of problem? So It's important to think about that. So like cat versus dog, that'd be a classification because that's like discrete labels. Meanwhile, number of fish might be a regression because you want to figure out like a number. And then same thing for mail or spam is like same as cat or dogs as classification. And so yeah, there we have it. So we just started machine learning today, I guess. Like we're for real. So now we start machine learning. We did supervised learning, and so for these next 4 weeks, I guess after this week, we'll be focusing on supervised learning. And so next topics is another form of regression. And so yeah, KNNs. I'm gonna stick with Maxwell and say that the AI. They can be argued to be ML, but I'll say the AI. But they're also really cool though. So they are awesome as well. But next topic is logistic regression, which instead of predicting values, we're gonna be classifying objects. So it's a different type of problem. And so yeah, thank you guys for staying out to the very end. I know we had like a lot of people at the beginning and they all kind of dipped, but thank you for staying till the ending. And as well as the code for today is Serbia. The GitHub is where the code is going to be in the future. So if you want these notebook, like the code notebooks, go to the GitHub. We'll have them uploaded. And please fill out the feedback form if you can. It really helps us figure out how to best run these workshops. And we already looked at all your feedback from the previous weeks as well. So yeah, with that, yeah, it's like 8:55, so I'll let you guys go. But thank you guys for all coming, and have a great rest of your nights or mornings, wherever you are.